Calculus can be used to optimize real-world situations. For example, you might have a limited amount of raw materials to make an object, for example, a box perhaps, and you would like to make sure that you are being as efficient as possible with the use of your raw materials by making the box that has the most volume given the restrictions of how much material you have. So that's the box problem. We're going to try to figure out how we can maximize the volume given a rectangular sheet of cardboard that's 20 inches by 30 inches. So we're going to start with this 20 inch by 30 inch rectangle of cardboard. And the way we're going to turn that into a box, and it explains it up here, 4 congruent squares will be cut from the corners. Okay? So it doesn't tell us how big to cut these. That's kind of up to us. And when we cut these 4 squares out of the corners, that's going to create some tabs that we can then fold. We can call this the left tab and the right tab. We can call this the front tab and the back tab. And each one of those is going to be folded along one of these lines. And then the bottom of the box is going to be this blue rectangle in the middle. And we've got a left edge and a right edge, a front edge and a back edge. So we're going to get some sort of box that looks like this, where this is the front. And then this is the right side. And then we've got the left and the back over here. Okay. We don't have a lid to this box. This is the back, this is the left. And these squares right here are thrown out, right? We don't need those anymore. Maybe we keep them so that they are little flaps that can get glued to the edge here, because otherwise we don't have anything to actually hold this box together. But those squares aren't going to contribute to the volume of this final box. All right, so let's take a look at this. We've got the volume of a box, and we all know, I think, that that's going to be the length times the width times the height. All right, the volume of a box is length times width times height, and that's too many variables. So let's see what we can do to eliminate some of these. So first of all, we know that we started off with a rectangle that was 20 inches by 30 inches. Unfortunately, 20 and 30 don't represent any of these 3 dimensions, right? They don't represent the length, width, and height. So what do they represent? Well, they represent things that get shortened, right? We have to take away this little chunk right here and this little chunk right here to figure out what's left on the left side. And that's going to be the same as this distance over here. So the length of this box is going to be 20 minus 2 different side lengths of the square. So we've got a side length down here, we've got a side length up here. So 20 minus x is going to be that length in the middle. So that length in the middle is 20 minus 2x. Right? We're subtracting x twice. Likewise, this width of the box. Hold on a second. I don't want that there. That makes it look like that's 20, but it's not 20. It's 20 minus 2x. We also have this distance right here, and that's also, it used to be 30, but we're going to subtract away this length and this length. And we actually have expressions for that already, right? Because since each one of these is a square, if this side is x, then this side is x. This side is x, this side is x. All of these squares are the same size for congruent squares. So the width is also going to be the original length, in this case 30. And we're going to subtract 2x from that one as well, which leaves us with the final dimension of height. Well, the height is when this dotted line and this dotted line fold together to make this edge of the box. That's actually just the side lengths of the square, right? That's equal to x. So we do have a volume formula that has 3 different things that are changing depending on how big our square is. But they all change dependent of one another, right? So if I change x, I change all of them. So length times width times height is just all of these multiplied together. X times 20 minus 2x times 30 minus 2x. So we can pick whatever x value we want to within reason, within the constraints of the physical problem. But the question is, how can we pick an x value that's going to make that as big as possible, make that volume as big as possible? So let's start by asking, what is the domain of this function? In other words, what are the allowable values of x? Well, I mean, obviously we can't have a value of x smaller than 0, right? If we don't if we in fact let x equal to 0, then we won't have any flaps to fold up, right? If x equals 0, we don't have a front, left, back, or right flap to fold up, and we get a volume of 0. But that fits, because if x equals 0, we've got 0 times 20 times 30, which is 0. Can x be as big as we want it to be? Well, no, because we've got these physical constraints of our original rectangle. So x could get bigger and bigger and bigger until the x's meet in the middle here. And if they meet in the middle here, then that's going to be, for the short side over here, is going to be 10, right? 10 and 10 gives us 20. Over here, the middle would be 15 and 15. But by the time we get to 15, we've already messed up this side over here. The most we can actually let x be is going to be half of that smaller side. So half of 20 is 10. And in fact, if we let x equal 10, what happens? Well, that means that we don't have a box anymore, right? We cut the 20s out, and we're left with no more left or right flaps. And that, again, makes perfect sense. If we let x equal 10, we get 10 times 0 times 10. So this would be the domain, and the extreme value theorem states that if we have a continuous function over a closed interval, then we are guaranteed to have an absolute maximum and an absolute minimum. Those maxes and mins happen either at the endpoints or at the critical numbers. And I think it's pretty clear that these endpoints, as we already discussed, are going to be minimums, right? They're going to be when the volume equals 0. Assuming we're never going to have a negative volume, which would not make a whole lot of sense, we must have a maximum value somewhere where there is a critical number on this function. So let's go ahead and find that critical number. When in doubt, set the derivative equal to 0 and solve for x. So I don't want to take the product rule of three factors here. So I'm going to go ahead and distribute this. We've got 20 times 30 is 600. 600 times x. We've got negative 40 and negative 60, so negative 100. X times x is x squared. And we've got negative 2 times negative 2 is positive 4. We've got x times x times x, which is x cubed. So we're going to find v prime, which is 600 minus 200x plus 12x squared. And we're going to set that equal to 0. These might be frighteningly large numbers, but at the very least we can reduce them for sure. 12 is 4 times 3, and while 3 doesn't go into 200, 4 goes into 200, and it also goes into 600. So we can divide everything by 4. Factor out of 4, we're going to get 3x squared minus 50x plus 150. And we could try to factor this, or we could jump straight into the quadratic formula. I'm kind of not feeling the factoring right now. I feel like we might want to go ahead and jump into the quadratic formula. So x equals negative b plus or minus the square root b squared minus 4 times a times c all over 2a. Right? So we've got 50 plus or minus the square root of, oh, I don't know, 15 times 12 doesn't seem too hard. It's going to be, did I do that right? Yeah, 180 followed by an extra 0, so 1800. So we've got 2500 minus 1800 is 700. Alright, so the discriminant is 700. It's good we didn't try to factor because 700 is not a perfect square. And then we've got that over 6. Alright, so let's see, 100 is a perfect square, so we can factor that out. And this actually doesn't look too terribly messy. Divide everything by 2, we get 25 plus or minus 5 root 7 over 3. So we get two different answers. So let's take a look at what's going on here. we have on our v prime line, we've got our quadratic, right? V prime is a quadratic, so because of the positive leading coefficient, we know it's a right side up parabola. So our left side is going to be the smaller of the two, 25 minus 5 root 7 over 3. And the right side is going to be the positive one, the 25 plus 5 root 7 over 3. These are values where the derivative of the volume equals 0. And again, with this idea that the parabola is coming down, hitting 0, turning around and going back up again, that means that we must have a positive, negative, positive. So our volume is increasing until we get to this number, then we start decreasing until we get to this number, and then we start increasing again. Okay. Don't forget this, though. X has to be between 0 and 10. So we can't go on to infinity. So I guess the only question is this value greater than 10 or less than 10? And you can use a calculator to figure out this is greater than 10. So irrelevant. Outside of the reasonable domain, so the endpoints don't matter here. We're looking at this as being the x value. This is the magic x value that we're going to cut the squares out at, right? Remember this quadratic formula is solving for x, and x is the length of the sides of the squares. So 25 minus 5 root 7 all over 3 inches is the number of inches we cut these squares out to be. And then to find that volume, the corresponding volume, we would take that crazy number and plug it into the volume formula. So this would definitely be a calculator question at this point, because, well, at least for me, I just don't feel like plugging that in to that cubic. And indeed, if we look at the graph of this volume function, scaled so that we can see the interesting parts, we can see that when x equals, I forget what our answers were actually, 25 plus 5 root 7 over 3. 25 plus 5 root 7 over 3. We get that point over there, that's a minimum, a local minimum. But notice that that value is 12.7, which is bigger than 10. It's not interesting to us. We don't care about that x value. I guess also, even if we did care about it, it would be giving us a minimum and not a maximum. On the other hand, if we look at the negative version of that, notice that that x value is going to give us 3.9, which is between 0 and 10, and it sure does look like it's hitting at that maximum point right there. So in fact, we can just figure out what v of that value is. We'll copy and paste, and we'll get a volume of about 1056. So so I'll just call this A so I don't have to rewrite it again. And then the volume at A equals about approximately 1056. And the units are, well, length is measured in inches, so volume is measured in inches cubed. And that would be the maximum volume attainable given the constraints of this problem.